Hello, my name's Andrew Lobb. I'm a mathematician at Durham University, and this podcast is going to be about the exponential function. I'm not interested in this talk, however, in talking about the mechanics of the exponential function, how you use it. Rather, I'm going to present a motivation for its definition at all. And the motivation comes from thinking about exponentials in general. So, first of all, let's think about this. This is 2 to the power 5. We should all know what this equals. It's equal to 32. And how do I get that answer? It's very simple. I look at the 2, I look at the 5, and I know that what I'm meant to do is take the number 2 and multiply it by itself 5 times, and I'll end up with 32. So this tells us that we know how to raise numbers to the power a positive integer. I just take that number, I take it the number of times I'm meant to take it, and then I multiply them all together. All right, so that's something we understand. How about negative powers? What do I mean by 2 to the minus 5? Slightly less obvious, but you'll hopefully remember that 2 to the minus 5 is 1 over 32. It's a 32nd. So what's the rule for a number to a negative integer? The rule for a number to a negative integer is, first of all, you think about the number to a positive integer, and then you take the reciprocal. So this is great. We know how to raise numbers to negative integer powers and positive integer powers. And we also know how to raise a number to the power 0. So let's think about that. So what is, let's write out this sequence. Okay, and figure out what they are. Well, 2 cubed is 8, 2 squared is 4, 2 to the power 1, that's just 2. I take a single copy of 2. 2 to the 0, don't know what it is yet. 2 to the power minus 1, 1 over 2, and this is 1 over 4. And the rule for getting the next term in the sequence, if I wanted to look at 2 to the 4, is just to multiply the previous number by 2. So that tells me that what has to sit in here has to be a half times 2, and when I multiply it by 2, I should end up with 2. So that tells me that what 2 to the 0 should be isn't 0, is 1. Okay, so this is great. So now we know, given a number, we can raise it to the power any integer, and it doesn't matter if the integer is 0, it doesn't matter if the integer is positive or negative. So let's push this a bit further. What do I mean by 2 to the power of fraction? What is 2 to the third? So we learn that this is the number that when we take its third power, we get back 2. In other words, it's the cube root of 2, and we're happy with that. All right, and what about 2 to a general fraction, where I've got some integer p divided by some other integer q? What do we mean by this? Well, we could mean one of two things. Turns out they're both the same. Using our rules for exponents, I can rewrite it in this form, in which case it's revealed that this is the qth root of 2 raised to the power p. Or equally, I can write it in this form, 2 to the p to the power 1 over q, in which case this is just taking the qth root of the pth power of 2. So this is it's great news. We understand how to raise 2 to the power any rational number. Rational numbers are those things that can be expressed as fractions of integers. But there's a big question, and a motivational question for us, which is going to be, what do we mean by 2 to the power root 2? And this is an interesting question because it doesn't fit into our scheme of things over here. And many of you will know that root 2 cannot be expressed as a fraction of 2 integers. It's what's known as an irrational number. So what could we possibly mean by 2 to the power root 2? So I'm displaying now proof that root 2 is not a rational number. It might not be the proof that you're familiar with if you already know a proof of this fact. But if you want to look at this proof and understand it, I think it's quite cool. So you can pause the video and try and figure out that proof. So how are we going to address this problem, raising a number to an irrational power? We're going to address this problem by defining something called the exponential function. And we're going to write it exp x. Quite often, you'll find yourself writing exp of x as e to the x, but of course, I don't really want to write this. If I could write this a bit fainter than this black marker, I would. The reason being that we've just decided that we don't know how to raise a number to an irrational power yet, so this doesn't make much sense for us. So what we're going to do is we're going to define a function, exponential function of x, that encapsulates some of the properties that we'd like to associate with a sort of exponent-like function. So what are these properties going to be? Well, the first property that we'd like an exponent-like function to have will be its value at 0. So we discussed that when we raise 2 to the power 0, and we didn't have to choose 2, we could have chosen any number. When we raise 2 to the power 0, we get 1. And the same should be true for this exponent-like function. So this is the first property that we're going to require it to have. Second property, well, I want the exponent function to look a bit like this, and I know how to multiply things like this. E to the a times e to the b is e to the a plus b is what we'd like to write. So in terms of this function, exponent of x, this translates to exponent of a times exponent of b equals exponent of a plus b. So here's two properties, and they're both exponent-like. We're going to try and define a function, exponent of x, that has this flavor of being e to the power x. Then we're going to require at least these two properties. So we're going to need a third property as well that isn't really exponent-like. So let me tell you about this third property. So we're going to imagine the sort of graph that we'll have for an exponent-like function. And we know one point on this graph already because we know the value of the exponent function at 0. It's 1. So this is the point 0, 1. And one thing we don't know is what's the slope of this graph at that point. So slope of the graph is about the differential calculus, right? The derivative of this function at 0. We haven't set in stone what this slope is going to be. So we're going to think about varying the value of e. I know that sounds like a bit of a dangerous thing to do. If we took e to be 1,000, this slope would be very steep, because for every unit that would move across in the x direction, this graph would have to multiply 1,000 times in the vertical direction. And if we took e to be very close to 1, we'd get a very shallow slope. So we're going to take a slope that's a sort of intermediate value. We're going to require that the slope of this function at 0 be equal to 1. So stated in terms of calculus, we say that the derivative at 0 is 1. Okay, so this isn't really an exponent-like property, but the first two are, and this last one we're just throwing in so that we can nail down this function. And really, these three things are the things that determine this function, exponent of x. So first of all, to see that, let's think a bit more about the derivative of exponent of x. And we're going to use some of these properties, in fact, maybe all of them. So let's think about the derivative of exponent of x at a point A. So another way to write this, sort of expand this dash, what I mean is I take the function d by dx of exponent of x, get a new function, and then I evaluate the whole thing at x equals a. That's what that means. So now I can use property 2 to rewrite exponent of x in kind of a cool way. I'm going to write it as the exponent of a times the exponent of x minus a. And then this thing, I take the derivative and then evaluate that at x equals a. And that's fine because this is just the same function as exponent of x by my sort of property number 2. And this is something that we know how to differentiate. So if I continue my equation up here, x bay is just a constant, and I'm differentiating a function of a linear term in x here. So the derivative of this is x bay, constant, and this is a function I have to take the derivative of, and then I evaluate at x equals a. So it's like this, and a minus a is 0. So this is the first derivative of exponent at 0, but this is exactly where we can use property number 3, because the first derivative at 0 we've decided is equal to 1. So this is just the exponent of a. So what we've shown is that when we take the derivative at a point a, we just get back the function, exponent of a. So if we're happier writing x instead of a, we can do that. So the first derivative of the exponent function is just equal to the function itself.